Our story begins billions of years ago in a time when the universe was still young and full of potential. Imagine a vast, swirling cloud of gas and dust stretching across the cosmos like a painter's canvas. This is the solar nebula, the birthplace of our solar system, where the seeds of planets and stars were sown. This nebula wasn't just sitting there. It was a chaotic and energetic place, filled with the remnants of exploded stars, each contributing to the cosmic dance. Within this swirling cloud, gravity began to exert its pull, drawing particles together with an invisible hand. Tiny particles of dust, remnants of ancient stars, started to clump together, forming the building blocks of future worlds. It's like the cosmic version of dust bunnies forming under your bed, only on a much grander, more magnificent scale, spanning light years. As these clumps grew larger, their gravitational pull intensified, creating a snowball effect in the vastness of space. They attracted more and more particles, growing larger and larger still, becoming the seeds of planets and moons. This process, called accretion, is the engine of planet formation, driving the creation of celestial bodies. Over millions of years, the solar nebula transformed from a chaotic cloud into a more organized disk, with a protostar at its center, our very own sun, the heart of our solar system. As the sun ignited at the heart of the solar nebula, its energy sent waves of heat and light outwards, creating a dynamic and ever-changing environment. The inner region of the solar system became a hot and turbulent place, filled with swirling gases and countless asteroids. Only heavier elements and dust grains could withstand these extreme conditions, surviving the intense heat and radiation. This is where Earth's story truly begins, amidst the chaos and collisions of the early solar system. In this chaotic environment, the tiny particles that had begun to clump together started to collide, forming larger and larger aggregates. These weren't gentle bumps, they were high-speed impacts, generating intense heat and pressure, enough to melt and fuse materials together. Over time, these collisions led to the formation of larger and larger bodies called planetesimals, which are essentially the seeds of future planets. Think of them as the building blocks of planets, the essential components from which planets like Earth would eventually form. As these planetesimals grew, their gravitational pull intensified, attracting even more material and leading to even more collisions, further accelerating their growth. This process of accretion, driven by gravity and fueled by collisions, continued for millions of years, gradually building up the mass of the young Earth. Gradually, a young, molten Earth began to emerge from the dust and chaos, a new world taking shape in the vastness of space. The early solar system was a chaotic and violent place. Planetesimals, some almost as large as planets, were constantly colliding and reshaping the solar system. These collisions were not just minor bumps, they were colossal impacts that could change the course of planetary development. It was during this period that a cataclysmic event occurred, one that would have a profound impact on Earth's future. Scientists believe that a Mars-sized object, which they've named Theia, collided with the early Earth. This event wasn't just a random occurrence, it was a pivotal moment in the history of our planet. This wasn't just a fender bender, it was a head-on collision of unimaginable force. The energy released from this impact was so immense that it fundamentally altered both celestial bodies involved. The impact was so powerful that it ejected a massive amount of debris into space. This debris consisted of molten rock and other materials that were blasted away from the collision site. This debris, bound by gravity, eventually coalesced to form our moon. Over time, these fragments came together, creating the satellite that we see in our night sky today. This is the giant impact hypothesis, and it's the leading explanation for the moon's origin. It provides a coherent narrative for how our moon came to be, supported by various lines of scientific evidence. The impact had other significant consequences for Earth. It tilted Earth's axis, giving us our seasons. This axial tilt is responsible for the variation in climate and weather patterns that we experience throughout the year. It also remelted much of Earth's surface and contributed to the formation of its iron core. This remelting process played a crucial role in the geological and magnetic properties of our planet, shaping the Earth as we know it today. The Earth, still reeling from the impact that formed the Moon, was a harsh and unforgiving place. Its surface was a molten sea of magma, constantly bombarded by asteroids and comets. Yet even in this early inferno, the seeds of Earth's atmosphere were being sown. As the molten Earth cooled, it began to solidify, but beneath the surface, volcanic activity was rampant. Volcanoes erupted, spewing out gases from the Earth's interior. These gases, primarily water vapor, carbon dioxide, nitrogen and sulfur dioxide, formed Earth's first primordial atmosphere. This early atmosphere was very different from the one we breathe today. It was thick and toxic, with little to no free oxygen. But it was a crucial step in Earth's journey towards becoming a habitable planet. It provided insulation, trapping heat from the sun and preventing the planet from freezing over. For millions of years, volcanic eruptions continued to pump gases into Earth's atmosphere. This process, known as volcanic outgassing, played a vital role in shaping the early atmosphere, but volcanoes weren't the only contributors. The early solar system was still littered with debris. Comets, icy remnants from the solar system's outer reaches, bombarded the Earth. These comets, carrying water ice and other volatile compounds, delivered vast quantities of water and gases to the young planet, further enriching its atmosphere. Over time, the Earth cooled, and the water vapor in the atmosphere condensed to form oceans. This had a dramatic effect on the atmosphere, removing much of the water vapor and leaving behind a denser atmosphere composed primarily of carbon dioxide and nitrogen. The stage was set for a revolution. In the primordial oceans, life emerged. These early life forms were simple, single-celled organisms, but they possessed an extraordinary ability: photosynthesis. These microscopic pioneers harnessed the power of sunlight to convert carbon dioxide and water into energy, releasing oxygen as a byproduct. This seemingly simple process had a profound impact on Earth's atmosphere. Over billions of years, photosynthetic organisms, from early cyanobacteria to vast forests, pumped oxygen into the atmosphere. Gradually, Earth's atmosphere was transformed. The toxic, oxygen-poor atmosphere gave way to an oxygen-rich one. This Great Oxidation Event was a turning point in Earth's history. It paved the way for the evolution of more complex life forms, including, eventually, us. While life was transforming the atmosphere, another remarkable transformation was taking place: the formation of soil. This process began with the weathering of rocks. Exposed to the elements, rocks are slowly broken down by physical and chemical processes. Wind, rain, and ice all play a role in physical weathering. They chisel away at rocks, breaking them into smaller and smaller pieces. Imagine the relentless pounding of waves on a cliff face, or the slow grinding of a glacier carving its way through a mountain valley. Chemical weathering involves the alteration of a rock's chemical composition. Rainwater, slightly acidic from dissolved carbon dioxide, reacts with minerals in rocks, breaking them down. This process is essential for releasing nutrients locked away in rocks, making them available for life. While weathering provided the raw materials, it was life that truly brought soil to life. As soon as bare rock was exposed, pioneering organisms such as lichens and mosses took hold. These hardy organisms accelerated the weathering process, breaking down rock and creating a thin layer of organic matter. As they died and decomposed, they added nutrients to the developing soil. This organic matter, along with weathered rock fragments, formed the basis of soil. Over time, more complex plants took root, their roots penetrating the developing soil, further breaking down rock and adding to the organic content. Insects, worms, and other creatures moved in, their activities aerating the soil and mixing organic matter with mineral fragments. From a swirling cloud of gas and dust to a vibrant planet teeming with life, Earth's journey is a testament to the interconnectedness of cosmic processes. The violence of Earth's early history, from the Theia impact to volcanic eruptions, played a crucial role in shaping the planet we call home. The formation and evolution of Earth's atmosphere, driven by geological and biological processes, highlight the intricate dance between living organisms and their environment. The oxygen we breathe, the soil that nourishes our crops, and the moderate climate we enjoy are all products of billions of years of Earth's evolution. As we look out at the vastness of space, we gain a profound appreciation for the rarity and fragility of our planet. Earth is a precious oasis in the cosmos, a testament to the remarkable power of natural processes and the interconnectedness of all living things.